So yeah, that introduction was written like more official one. But if you want to chat about how to build cybersecurity company in the US or in general entrepreneurship in cybersecurity, would be happy to chat with you, but that will be kind of a separate discussion. Today I will talk more about the infrastructure security and what does it mean. It's actually a very nice highlight from the previous talk about satellites and like how many different infrastructures do we have and how they integrated to our life, like IoT and many things else. By the way, who wants to do satellites research can look in eBay. I've done it a couple of months ago. You can buy decent satellite equipment for the research on a decent price there. So definitely recommend you to watch. And some of you who may not hear, or maybe everyone heard about pagers, what happens there. It's kind of all related because we have devices, which is basically around us, all of that like laptop, server, networking devices, phones, and IoT devices, satellites, all of these. So that would be kind of part of my talk. We'll talk about how that all devices are secure. And I've started my career many years ago from application security. And I've done some browsing exploitation and kind of followed that a little bit over many years. And I saw how much progress we've done in application security and how expensive it is to buy the fully functioning RCE exploit for browser with the sandbox escape and everything. And that was kind of one of my interests many years. And then I was basically start thinking about, do we have all of these best practices to as a part of the technology stack, which is basically the technology which is we have our workflow running on top of them, like things like operation system and the firmware and the hardware and bootloaders and drivers, all of that like foundational piece when you kind of build in your workflow. Do we have all of that security there? There's a couple studies we will have during this presentation about this. Like a spoiler alert, not as good as the browser security. So let's start with a little bit of what this infrastructure is. And depends who you will ask, it will give you the different answers. If you will ask an application developer, he will say, everything I use is infrastructure for me. Libraries, operation system, Docker container, all of this. But if you will ask a DevOps guy, and he will say, yeah, infrastructure is my cloud, cloud resources, compute resources. So he will basically will think about infrastructure slightly differently. He will think like more like a lower level than the application developer guy. But then if you will ask a hardware engineer or data center engineer, someone who kind of build the hardware in order to support this cloud, private cloud, public cloud, hybrid cloud, he will tell you that infrastructure for me is the devices and configuration of the devices. So we don't have that kind of clear what is infrastructure. In my presentation, I will focus more on the device level, like very low level stuff. But some of the concepts you can reuse to some other type of infrastructure. So for us, infrastructure is things which is produced by vendors like Dell, Lenovo, HP, Supermicro, whoever. They produce all of this great hardware. And that hardware become quite very important. And you may think, okay, but that hardware, it's not complicated. It's kind of very simple hardware. In reality, in the last 20 years, we see that complexity growing of the devices, of that layer. The reason is that we won't manage that thing very quickly. We won't manage that remotely. We want to get time to market very fast. We wanted to build very quickly. It will push us to reuse a bunch of stuff. It will push us to reuse Linux a lot. And then you basically package up many different Linuxes to different devices in order to build your infrastructure. When you package up many Linuxes, you basically get many problems because you have to update, you have to configure, you have to manage all of that kind of your own code and open source code and over the time to all of that. So it becomes quite a complicated problem. And the visibility to that layer is not as great. So if you wanted to say, how can I run integrity of these devices? Can I see if the driver will not basically blue screen? Or can I see if the bootloader basically has the right configuration? It's quite a complicated problem because not always you can read it. And whenever you can read it, always never, you basically have the ground fundamental rules, what it should look like. So it basically entire set of the research, how would you recognize that? And today I will talk about like a very traditional type of infrastructure. It will be networking devices like Cisco, Juniper, Arista, Aruba, but we will focus on F5 mostly, and servers, like a typical x86 or ARM server, which has basically a management interface, call it BMC, baseboard management controller, which is basically kind of a remote way to manage your server. And basically that's a two area where I will focus today. In both of this area, we found remote code execution vulnerabilities, which can be exploited as the initial vector to the infrastructure of the enterprise, or as the lateral movement and more kind of persistent need for the attacker. And in both of this area, you may ask, okay, what is common between them? It's actually common that they basically use Linux type of system, and they reuse a bunch of code, and they put a bunch of code on the top of that, which basically extend the attack surface for these type of devices. And then when the users put their devices in network, it could be actually front line device sitting and watching an internet, they basically extend the attack surface. So attacker can actually go not to compromise browser and get the users, but he can basically watch and see what kind of devices specific enterprise use and build very custom attack against the devices. So that's what we observe in a couple last years. Yeah, I will skip about myself. You can find me on internet, GitHub, all of that. So we will talk about networking devices. So for me, the entire time frame was split by two phases. Before SolarWinds and COVID and after. Before SolarWinds and COVID, SolarWinds incident when we basically got supply chain attacks on SolarWinds, not many people put a lot of discussion, but SolarWinds is the software to manage networking devices. So whoever owns SolarWinds software owns all of the devices on the network, managed by that software. So which is quite a nice use case, which is basically attacker also can utilize. And basically the time split it to me in a way that we didn't see quite a lot of attack through networking devices before 2020. So you can see a couple of them, like some of the national state attacks, but not quite a lot. And then when you watch for things which happen after 2020, you will see quite a lot of them. The reason is that, first of all, the workflow changed. Everyone started working remotely, VPN, all of these load balancers needed to be frontline in internet. And then they have a management interface, which is nice to have also on internet. And then basically that management interface, in many cases, written in very poor custom code, which you can basically, very basic OWASP 10 web vulnerabilities present within that interfaces, which we will see in this presentation. So that basically something very interesting to observe. And also you can basically take any of that studies, like from Ivanti, Fortinet, pick any, and you can basically study the exploits which will fit inside basically a tweet, the 140 bytes symbols, and basically you can figure out like how does that exploit work. And there was quite a lot of examples in the wild and proof of concept. You can find them on GitHub. So that's the area of interest. So as I mentioned, the complexity of this device is growing quite a lot. And in many cases, they try to use neither Linux-based box, FreeBSD-based box, and basically put quite a lot of functionality there without kind of thinking about like, some vendors, they don't think a lot about how to properly secure that system. And from the basic SDLC practices like do not put everything under root, to basically kind of, you need to do the pen test of your device, similarly as you need to do pen test in 90s of your website. So you done the pen test of your website, but you didn't do the pen test of your devices when you produce them. And we basically see a lot of vendors, they may improve some SDLC, but they didn't kind of done to the level of, okay, I will be treating this device as externally servicing component, which I need to basically do all of that testing as I'm doing for something else externally facing. And if you open up many network devices, and this you can see here Cisco and F5, you will see it's networking device. You think it will be a special hardware there. It can be actually some special hardware like FPGA or some ASIC to manage a specific workflow of network device. But in reality, network device is just a server. You can buy it from Supermicro if you're thinking about to build your own network appliance and you're thinking that your volume will be more than 5,000 devices, you can actually literally call Supermicro and say, hey, I want 5,000 servers on this specific configuration, on this specific firmware, and they basically serve you this customization. So you can basically produce your own appliance that cheap, that easy. And what happened basically in this case then, many vendors doing exactly this. They buy in Quanta or Supermicro or some couple other vendors, and they basically package up software, put the logo on the top, and selling you as a very special type of equipment. But in reality, when you open it up, it's just a server. And first of all, it has all of the security best practices about the kind of how to protect server with respect of the BIOS update, BMC update, all sorts of like component updates. But also you need to make sure that you have secure boot, secure update, and all of that basic hygiene of the hardware. And you also need to think about the hardware attacks, because basically everyone who has access to these networking devices with the physical access could basically plug the SPI, basically DD programmer to the SPI chip and rewrite BIOS firmware or BMC firmware. So that's kind of very nice in general. If you have networking devices you want to experiment with, always open up the box and find what controllers inside. And you will be surprised at how basic they are and how less thinking vendors put around how to secure that components, that chips, the configuration of the chips, and build like a very strong security from the supply chain perspective, as well as from the remote code execution perspective to update the components, manage them with full respect to all SDLC practices. So yeah, there's a couple examples here. So when you got this device, you can get shell. In many cases, the shell could be part of the functionality. So you don't need to basically root this device. There is a shell. It may be limited, like BusyBox doesn't have some commands, but it may be there. In case if it's not there, you can actually, in many cases, root this device. And we actually done very nice experimentation when you can root a virtual appliance. So basically, in the modern world, you have physical devices, but in many cases, the vendor create a virtual appliance copy of that physical device. And that one has just like a file system where you can mount and drop the shell and basically do your experimentation. So one way or another, you would like to get a shell. And for like Palo Alto network devices, you would inject the shell. In F5 devices, you will just get the shell out of the box because it's part of the functionality. And when you got the shell, you will be kind of, oh my God, I'm come back from 90. So like all of these like flashbacks about like, okay, it basically everything running this root, no ASLR, no DEP, and all sorts of like injections, type of command line injections, things like that. It's still coming back on that environment. That was kind of very interesting for us to observe all of this coming from many vendors. And again, we will focus a little bit on F5. So it doesn't have enough visibility inside. So as I mentioned previously, you cannot clearly do forensic of these devices without spend extreme time to figure out all mechanisms to get access to file system, to get access to memory, to get access to different type of firmware. So it takes time to build the proper visibility for these devices because it was not designed to easily do the audit and provide integrity of the device. To be work. And as I mentioned, like for the browser security, we got a lot of testing, we got a lot of memory saving checks, we got a lot of things there. What we done for the devices? Actually, for the devices, the recommendation is not bad. You use the same mechanism, you build the browser security. First of all, use sandbox. Put all of the things in a sandbox, make it very hard to escape from sandbox, things like that. So use Docker, use all of this fancy sandbox mechanism. And then to prevent the memory corruption, use basically the memory the languages which is basically doing some memory safety, like Go and Rust and things like that. And you kind of protect from many, many attacks. That was recommendations, very similar to kind of how we adopted control flow integrity. to the application level, but from the point of the devices. And you can do that for the devices as well. So what is important is that that was done by not all of the vendors. So you still can find a lot of things which is you will see in BMC when that type of isolation was not implemented. But that's a recommendation. We will talk about the vendor which did implement this and vendor which doesn't implement this. So basically F5. So F5 is basically a load balancers type of hardware. Some of you who study F5 from the long time, it was replacement from very expensive hardware when you basically use slightly cheaper hardware, but more like a commodity hardware with a software which is doing almost the same functionality as the hardware. It was a good differentiator from the market, but they use commodity hardware, and that kind of was one of the source of problem. And there was basically some vulnerability found on that stack. And after that, they basically decide to re-implement all of that stack again in 2023. This F5 Big IP, a new implementation, has quite a lot of changes from the previous implementation with good security practices. And that security practices actually does implemented all of that isolation through Docker. So when you're running either management or the real F5 Big IP device, both of them has a lot of Docker images. Inside the Docker images, you have the Go compiled binaries, which is basically quite good isolation. So first of all, inside the Go, memory corruption is hard to basically exploit if you don't have a serialization, deserialization problem of the objects. You will not figure out easily how to exploit that. And then if you do that, you need to do a privilege escalation and escape from the Docker. So it's an interesting, much more interesting and better architecture than you will see in 99% on other networking devices. So all respect for them to doing that. But you still wanted to explore what's going on in these devices. You're still kind of thinking that maybe some basic stuff left. So you got the shell, you basically watch for every Docker images, you get the binaries, and you start kind of thinking about, okay, what I can basically test out? How can I basically see if there's maybe vulnerabilities there somewhere? Yeah, so I've touched on that a little. So you're thinking, okay, what left? Logical vulnerabilities left, OWASP 10 pentests left. You wouldn't focus too much on fuzzing and basically build some routine for the binary analysis or memory corruption type of vulnerability. You kind of put this as a side, maybe you will do it later, and you start with very basic. Okay, I'm a pentest guy. I will try to find some things like SQL injections and command line injections, things like that, and I will see what happened there. And that's what exactly was done. Basically, we just kind of spent a couple days and kind of thinking about this device as the web interface of certain website and certain functionality, and we just do basic pen test. We found a couple injection type of vulnerabilities. One of that would allow us to leak the password, the admin password of the Big IP appliance or management system. And another one is basically would allow us to manipulate like with the SQL database. That was quite very interesting and very basic. We spent for that research maybe less than a week, and we got basically leaked hash. And that hash was basically having a weak encryption. So with the good kind of GPU cluster, you can basically brute force it quite fast. So that was quite interesting. We basically have a demo, and everything is much more detailed form already presented on a Black Hat. Yeah, is that you basically doing the basic pen test on a device, and you kind of found something very interesting, exploitable, reliable, and could be basically used at attackers to get the initial access to the infrastructure. So yeah, so OWASP 10, basically things which are still coming up. And you may think we kind of passed this, but not on a device level. So the infrastructure is not protected from the OWASP 10 vulnerabilities. So yeah, paying attention to basically how we build our firmware and making sure that if we will implement the code for the firmware from the vendor perspective, we always basically come back and basically put inside the SDLC the validation of things like SQL injection and then the command line injection and so on and so forth. So yeah, we reported this vulnerability. Not all of them was fixed, so some of them was left over. Vendor has their own way of thinking what should be fixable, what is not. Quite big discussion about that. Maybe for some other time, how properly communicate to vendor in order to convince them to fix all of the findings, not the only one they believe they need to fix. That's kind of where demo of the exploits always helps. So that was basically the example when we basically run analysis of a 5 device. You can actually do exactly the same for all of the IoT devices and other networking devices. Most of them are Linux, and most of them has web interface. They neither have UPnP protocol or they have a basically web interface protocol, things like that. And you, in many cases, will be close to the same results. You may find the remote code execution vulnerabilities. If that's not the case, you can basically do a little bit more on the hardware and firmware analysis. When you open up the device, you can dump the firmware. And in that case, almost always you will find that neither secure boot or secure update doesn't implement properly, and you can build implant for this type of the devices. So that was always the case. We didn't find a device which is hard to compromise at this time. Moving a little bit to kind of server side. So that was like networking devices, and you might think, okay, but servers definitely done better job. We have servers forever, and they kind of the foundational of our data centers. And especially in Gen AI world, when we basically buying a lot of GPUs, somehow we need to manage that GPUs, we put them on the servers, and then we basically kind of plug and enable a lot of data centers. And in order to manage all of these data centers with GPUs, all of the servers, you basically use BMC, as I mentioned, baseboard management controller. It's a separate chip. Normally, it's basically ASPID chip, 2500, 2600. That chip actually started implementing secure boot recently, but that chip is running in Linux. And in many cases, that Linux actually written up not by the vendor of who is producing that server, but by the vendor who is producing a software for that server. It's called AMI, and MegaRAC BMC from implementation from AMI is the one where we found the remote code execution vulnerability. So a little bit about this. The Gigabyte leak, for some of you who is not familiar, there was a compromise of the Gigabyte company, and there was a leak of the source code of them. Basically, you can download quite a lot of Gigabyte firmware and run analysis of that. Definitely recommend you to do this. It's a very nice exercise to understand how does vendor create the firmware and how does the package and develop this. Will give you a lot of insights how to find vulnerabilities in this type of infrastructure. So that's kind of one of the examples of how does it look like a lot of files, and they structured like in a way that some of the directory represent the modules inside the firmware, and the way does the firmware design it is actually the code migrating through multiple organizations. There's something which is called reference implementation, and then this reference implementation bought by some company in order to build the final device. And when you buy in a reference implementation, you can actually put more code in. So what does it mean is that if there's any vulnerability in reference implementation, it's very hard to trace it down to the specific implementation, because you may think about like there's like one-to-one mapping, but there's not one-to-one mapping. Basically, the implementation from the vendor.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast, I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior.
How does the firmware implement it? You will figure out that understanding how the code migrated from one organization to another give you a lot of good understanding if you will find vulnerabilities, who would need to fix it, and how this will affect the entire ecosystem. The vulnerability we found actually affected more than 10 vendors. But when we originally found that, we found just in one. And we didn't even know how many other vendors use the same code. It was even a surprise for us. So when we found this, yeah, Gigabyte is affecting, there's Lenovo affecting, but when we figure out that there's more than 10 affecting, that was quite interesting. So anyway, whenever you're doing the analysis of the firmware and hardware, reference implementation is extremely important concept. And sometimes you can buy very interesting stuff if you go in to buy a development kits which has a reference implementation with that. For example, for ASPID BMC, for Qualcomm devices, you can get very interesting hardware which will give you the good source of tools and mechanisms to find vulnerabilities. Anyway, let's move forward very quickly. So basically, you got the first impression of what's going on here, and you basically, first of all, always looking for things which is like a debug capabilities or kind of a backdoor type of functionality. And in source code, it's easy to, vendors always have a debug capabilities. So it's very interesting to find that and see if it's enable or disable, and that could be a quite interesting area for you to look at from a code. So when we basically start analysis, we figure out that the code is quite ugly. It has a lot of redirections, a lot of like conditions when it has 10 layers of indirections. Normally, when you're basically thinking about like how to write the code secure, you're also following the best practices of the development to be easy to audit. That was not the case. And we basically we know why BMC exists, and BMC exists to support a lot of management functionality, like virtual devices, like when you basically go into the BMC, you can literally see a screen of the server. So that's one of the functionality is there, implemented through virtual devices. And there's quite a lot of others, including a couple very important one, which is Redfish and APMI, which I will mention in a second. So you will figure out everything running as a root, so which is basically by itself already will surprise you. Then you will inspect the ports. That's actually you're doing from the live devices. So you have a source code and you have a live devices. And that's how you combine this knowledge together. So then you will scan, you will see that there's web UI and there's Redfish. So web UI is basically what admin will use in order to log in and see some information. Redfish is the interface he will basically program in order to build some automation. For example, the firmware update flow or some temperature checks or whatever. And that basically it's RESTful API with the JSON schema. So quite nice interface. A lot of bugs can be found there. And basically it may be SSH there. It's not always, but the vendor may leave it, so you can get that as well. So how would you start your research? It's very simple. First, you will see who calls system, and then see if you can basically pass any parameter to system. It's very, very basic. It's like something which you always do when you do analysis of this type of boxes. And surprisingly that we just ran this grep on system and found one of that, which is actually you can inject the command line. That one actually was post-authentication. So basically, if you get post-authentication on BMC, you can basically inject the command line here to do code execution and basically persist on this. That was very interesting. We call this vulnerability BMC version 1, BMC version 1. It was presented last year. That was a very good way to basically start. The important part here is that, again, this code is running on isolated chip. And if you corrupt the firmware of the chip, the entire server will not boot at all. So the highest privileges on a server is in BMC. And that one basically allows you to run code execution there. Pre-authentication, post-authentication. Pre-authentication will be in a couple slides. So yeah, that's basically all things you need to do is basically run this very tiny script in order to do that. And you bypass the spaces in a command line in a request, so basically quite trivial to exploit. So then when you got the shell, you can basically start watching what is inside. So as I mentioned, getting shell is quite important. You got it and you start exploring. You found that you found the hash of the admin. You basically can brute force it and found that, hey, they basically left the default password for, yeah, they left the default password for the super user. So basically, it may or may not be enabled by vendor. Remember when I said reference implementation can be modified by vendor. So basically, this, when it comes to the vendor, may be disabled. We found instances when it was enabled. So quite good vulnerability there. It's actually was supposed to be fixed 10 years ago, but for some reason we still see instances when it was not fixed. And then we basically, okay, we got code execution, we got shell, we got root, we got the default password. All of this is nice, but it's not really giving us remote code execution, which makes this slightly harder to kind of chain it to the full attack flow. And that's when we start exploring, okay, how does the redfish works, and how does web UI work, and how they kind of coexist together. And what we noticed is that there was another basic vulnerability which allow you to run pre-authenticated code execution. Everything starts from here. We basically start looking for things like, what is this USB address in the source code? And what we figure out that, kind of going to a couple presentations back about BMC, you can watch like USB Anywhere, another presentation from what we presented in the past. But the idea is that you have two interfaces. One is the remote interface, which is basically your server has the Ethernet port and that remote functionality running there. But also the same functionality is accessible through the host. So the server you basically running has the operation system, normal operation system, and there's also interface to communicate to BMC through the host. That communication done through IPMI, through some other interfaces. In that specific implementation, it's done through a specific virtual USB device. And that virtual USB device is basically a virtual USB Ethernet adapter, which has its own IP address. What it means is that the BMC itself has kind of a two network. One is the network from the external, and one is the network from the local host, which it does see like the USB device. With the IP address, normal IP address, like it's like a Ethernet controller. So that was a key thing, because later on we will say the remote request, please look like a local request. And that was the key to do remote code execution. So because the local request doesn't require authentication, and when you send it basically remotely, you bypass an authentication and you just run the command from the admin privileges. That was kind of the key of the entire exploitation. It was very trivial. So basically, you start exploring more, and then you notice that BMC has the entire Lua interface. And basically, inside that Lua interface, you will see that Redfish implementation is implemented in the Lua. It's kind of strange, but whatever. They decide this way. You will find the exact check here will be basically that it basically comes from the host, and it basically checks if basically it goes through USB or not, and then if it is, it basically tells that it's from host, trust this request. But the information about the host inside the HTTP header, which is controlled by attacker. So attacker will tell, here is the host IP address, and then BMC will think it comes from the local interface and will not check the password and would allow the command just to run. So yeah, so basically that's the first time when we basically showing up the full exploit. Basically that's how you basically inside the header you provide just one field of the host, and then the rest is the standard request, and this request not supposed to go through, because this field not supposed to be here, because from the remote you should always request the password and you never should skip this. But with this implementation between the HTTPS service and the Redfish service, that field inside the header, which is attacker can control, and when he can control it, he just put it here, and that's it. So all exploit in order to infect the BMC is this one. And then when you infect one BMC, you can actually distribute and infect all of them, because in most, all of the configuration, all of the BMC sits in one network. So because normally it's very hard to manage BMC if they will sit in different networks. So infecting one, you infect all of them. And again, this code running in a special controller inside the server, by compromising this, you can get full control on the server. So that was quite nice. So when you got this, you actually can run any redfish command. But what you will do with the redfish, how to do code execution. So in order to do code execution, actually that's one about how does the two services didn't agree how to validate the request. And there's like CV on all of that. So the interesting part is here. So when you basically get that access, because remember I mentioned that you have Lua interpreter inside the BMC, when you have a hidden command in order to upload your own Lua script. So after you get remote code execution, you can upload your Lua script and you get your full code execution with the root privileges on the BMC. That's exactly what it takes to exploit this to the full root of the BMC on that class of the BMCs. Yeah, there's another CV assigned to this. As I mentioned previously, it just misunderstanding between services within the BMC, who should validate what, and why this field was not validated, why this field even exists in the first place. And combining these vulnerabilities, you can actually get full remote code execution, privilege escalation. You actually don't need to have privilege escalation because you have root. You can do just persistency, and persistency is also there because you actually could modify the file system. So you basically kind of exploiting two vulnerabilities. One will be bypassing authentication through that host field, and another one is Lua script. That's it. And that basically would lead you to full access to the BMC with the shell. Then you can basically make a lateral movement between BMCs. You can control host. You can scan memory, send the data through the stack of the host, or you can send the data through the stack of the BMC network. So both of them will be available for you at that moment, as well as you can just put the system, you can just break the system. You can put the infinite loop, and that system will just break and will not work. So basically, there's a lot of other area which we didn't explore well, but they can be explored more. There's a bunch of binaries implementation which we didn't do full analysis of, assumption for future research. We found a couple other vulnerabilities. One is user enumeration. Another one is basically when you're resetting the password, attacker can actually send the new password faster than the real user, and you would basically get the admin password at that small time window. Quite nice, interesting. Depends on the configuration, so may not be applicable. And as I mentioned, this is the vendors was affecting. So it basically it's 17 vendors. When we found this vulnerability, we actually found for 2. And somehow from 2, it grew to 17 without us to understand what's going on, because that's how much reusability that code gets from the AMI MegaRAC to all of these vendors. I was surprised with some of them. I was not even expected. So yeah, basic vulnerability, as you saw, in networking devices and a server, it's basic OWASP 10, like confusion of the fields versus like a command line injection, and get you full control of very sensitive pieces of your infrastructure. That's pretty much it, what I wanted to cover for today.